with was A5, right? So this is just simply, here are some pictures of different orbitals. And then the question is, to assign the possible quantum numbers, the names of the atomic orbitals, and then draw the nodes on those orbitals. So, starting off, right, if we look at this first one right here, we have A. So what we can see is that we just simply have like a blue ball, right, that's sitting right at the center of the XYZ coordinate plane, right? We don't see any red. It's only a blue ball. So that should tell us that what we're looking at is an s orbital, right? Because it's a perfect sphere. It's a perfect ball. So we already know it's an s orbital in this case. So we know it's an s orbital. We know then that means that L is going to be equal to 0 in this case, right? And then M sub L has to equal 0, right? Because if we're thinking about the definitions, right, N is any positive integer, right? The values of L can only be from 0 to N minus 1. And then the values of M sub L can only be negative L to 0 to positive L, right? So those are the conditions that we have to work with. So looking at that right there, right, again, we know it's an s orbital because it's a perfect sphere that's completely centered at, the center of the XYZ coordinate plane. So we know that much. Now, again, because we don't see any, other red in this specific case right here, right, that's going to tell us that we don't have a node, right? That's telling us that there's no nodes that are present, whether they're angular nodes or radial nodes. There's none of them there, right? So if there's no nodes present, then that means that n has to be equal to 1 in this case, right? So n is equal to 1. So that tells us then that this is the 1s orbital in this instance. Moving on, right, if we look at B, the first thing that we should be able to see here, right, is that we have both a red lobe and also a blue lobe, right? There's the two different, colored lobes, right? Two different balls. The next thing to look at, right, is that you can see that they aren't stacked on one, kind of like Russian dolls, right, where they're stacked inside of each other or anything like that, right? They're next to each other along one of the axes. And so because they're along one of the axes, we can see then the point where the red switches to the blue is along that XZ plane, right? So we have that XZ plane that's cutting it in half. And because it's cutting it in half, right, and then that means that the node is at the 0 point for the system, right? That's going to tell us then that we have one angular node, right? So we have one angular node in this case. Right, and if we were to draw that, let me switch colors so that way, right, we can see then that node is on the XZ plane in this instance. So we know we have one node, right? We know it's an angular node. So if we have one angular node, that tells us then that L is equal to 1, right? Because the number of angular nodes is equal to the L value that we have. And so the next thing that we know then is then if L is equal to 1, that we're working with a p orbital, right? So we're working with a p orbital in this case. Now, there's two things then that we can focus on now is one, do we have any radial nodes, right? To figure out what our n value is, right? What is the principal quantum number in this instance? And so looking at it, right, we know it's a p orbital. And so if you're going to have a radial node with a p orbital, what you end up doing is then having additional, phase changes, right? Switches of a blue lobe to a red lobe that occur not at the origin, right? Not at, when, x, y, and z is equal to 0. Right, and the way that kind of like always like pictorially looks, the way that always looks is it looks like there's just basically like like a mushroom cap or like a hat or something like that, right? That's sitting on top of the orbital, right? That we would usually expect in those cases, right? And we don't see that, right? So there isn't a radial node, there isn't a node that occurs further along one of the axes in these instances, right? So we know there's no radial node. Right? So one easy thing that we can do to figure then out what the principal quantum number is that the total number of nodes is always going to be equal to n minus 1, right? So n minus 1 is going to dictate how many nodes there are in these cases, right? And then the total number of nodes is also just simply equal to, right, the number of angular nodes plus the number of radial nodes. in these cases. So if we know that radial nodes is equal to 0, we know that angular nodes is equal to 1, right? Then that means that the total number of nodes is equal to 1 in this case. And so if, the total number of nodes is equal to 1, then that means that n minus 1 is equal to 1. Move everything over, right? That means that n has to equal 2 in this case. So we have n is equal to 2, right? So if n is equal to 2, this is a 2p orbital. Now the question becomes, what is, the type of 2p orbital that we have, right? There's the 3 different types. There's the x, the 2px, the 2py, and the 2pz. And then, that will then dictate what the m sub l value is. Now, there's only one that you can easily, on your own, always figure out what the m sub l value is, and that's the one that's primarily along the z direction, right? So the z direction, that one is always going to be m sub l is equal to 0. The moment you have an m sub l value that's, positive plus or minus 1, plus or minus 2, right? That starts to get x, y, and z components that go into it. The challenge then is like which one is, because you can have 2 different types, right? So in this case, you can have 2px or 2py, where you're not, primarily in the z direction. Right. So then the question becomes, well, which one is which? And that really has to do with the perspective of how you're approaching the problem, right? In terms of where you're setting, your 0, theta and phi in those cases, right? So some people, set y as the z, the y-axis as the 0 point. Some people set x as the, the 0 point. But no matter what, right, they're always going to be then, not 0. And then, there's always going to be a combination where you have the 2 of them together, right? So in the case of the 2px and the 2py, right, they can be either plus or minus 1. It's just simply a matter of, the perspective of how you approach it. So in this case right here, right, so m sub l can either be, plus or minus 1. And I know on the answer key, I deliberately said, one of the values, right, because I always set everything towards the y-axis. But again, if you've taken any physics classes, some people always start off and have, a right-handed coordinate system, right? And then other people use a left-handed coordinate system, right? There's always, it's a matter of perspective, if you go and you think about coupling constants, right? Some schools of thought have them be negative. Some of them have to be positive, right? In terms of like what the ferromagnetic interactions are. This is something from Chem 500, right? But it's always just simply where you're coming from. But that doesn't necessarily change what the answer is, as long as you're staying consistent in those cases, right? And so, but again, the only thing that you really have to remember in terms of the axes, right, is that if it's primarily the z component, right, that's going to be the m sub l is equal to 0. And then all the others then just slowly like go until you get to the maximum value that you can have for m sub l. So right, in this case, it's plus or minus 1, right? Then that's going to be, directly on the x-axis or the y-axis. So that's the, the thing to think about there, especially for this class. Does that all make sense for everyone? Hopefully. Cool. All right. So C, right? So this right here. Okay. So, and then sort of last thing to do, right? So if we're looking at this orbital right here, right, we can see that the 2 lobes, they're sitting along the y-axis, right? The axis that's like, drilling through that orbital, right, is the y-axis. And so that's what makes this right here, the 2py orbital in this case. Moving on to the next one, right? The first thing that we're looking at now, we can see that we've, doubled the number of lobes. We're now at 4 lobes, right? There's 2 blue, 2 red lobes in these cases. And so again, what we can see is if we're looking at it, we can see that we have one angular node that includes the z and the y plane, right? Right there, right? Because that cuts, you're going from, this red is going to jump over to that blue, right? This blue is jumping over to that red. Then the next thing that we can see, right, is that we also have another plane that's bisecting, right? That's a node that includes the xy axis, right? So that is that includes right there, right? So you have 2 angular nodes. In this case, right? So if we have 2 angular nodes, that tells us then that L is equal to 2. The next thing that it tells us, right, is that we're working with a d orbital, right? Because d orbitals have L equal 2 in this case. So the next thing then to look at, right, is do we have any radial nodes? And so again, as I had mentioned, radial nodes do not occur at the at the origin, right? They occur further out, right? And they're just, a radial node is essentially a huge invisible sphere that like cuts the lobes and changes the phases in these cases, right? And so spoiler, none of these that I have for problem A5 have a radial node, right? These are all strictly zero radial node orbitals in these instances. Now, so that's just the thing to think about. Right, so we have that. We can see that we don't have any radial nodes, right? Because there aren't any like little caps on all of those different lobes, so we don't have to figure that out, right? So we have 0 angular nodes. Oh, sorry, not angular nodes, radial nodes. Right, in this case. And so if we have 0 radial nodes, if we use our formula that we have over here, right, the total number of nodes then is equal to 2. So if total number of nodes is equal to 2, then that means that n has to equal 3 in this case. Right, so that means that we're looking at a 3D orbital. Now now the last thing, right, is the m sub l value in these instances. So the way to approach this, right, for d orbitals and then also f orbitals and so forth is you can just simply memorize them. Right, that's the probably the easiest way to do that initially. But the next thing to look at is to think about, okay, well, do you have, where do the lobes reside in this system right here, right? Like in terms of like what axes are participating. And so if we're looking at this one specifically right here, right, we can see that each one of those lobes of the orbital are, in the middle of the xz plane. Right, they're just these balls that are hanging out, in between the xz plane. So that's telling us that the wave function in this case right here, right, has both an x and a z component to it in these cases, right? And so if it has an x and a z component to it, then that means that what we're looking at is the xz orbital in this case, right? And so if it was rotated by 90 degrees, right, and then those two lobes were sitting in between the y and the z axis, right, that would be then the 3dyz orbital. And so now in terms of the m sub l value, right, because there's still there's 3 possible degrees of z contribution that you can have for a d orbital, right? You can have it completely involved, right? So that's going to be then the 3dz squared, right? And then you can have the ones where it's partially involved, right? So that's going to be your 3dxz and your 3dyz. And then you're going to have the ones that are completely on the xy axis where you don't have any z contribution. And so those are going to be, your 3dx squared minus y squared and your 3dxy in those cases. And so again, right, because it's, there's 3 different degrees, right? So this is 0, 1, 2 in terms of the m sub l values. Because we're at that 1 point right here, right, the m sub l value can be plus or minus 1 in this instance. So yeah, so that's A5C. So D, right? So if we're looking at D, what we can see right here, first off, this is a really clear way of looking at it, right? You can see there's a very clear plane, right, that's cutting our orbital in half and making those 2 different lobes with 2 different colors. Right, and so that's in the YZ plane in this case right here. So we can see right here, right, we have one angular node. There's no other ones. So that tells us that L is equal to 1. So this is a p orbital. Again, looking at it, right, we don't see any radial nodes, right, because the lobes don't have any caps on them that have, the opposite color or anything, right? So there's 0 radial nodes. So if we only have one angular node, total number of nodes now is equal to 1. If you have that, that means that n has to equal 2, right? So we're looking at a 2p orbital in this case. And so then now, right, what we're looking at is if we look at the directionality of the orbital, right, we can see that it's directly along the x-axis in this instance, right? The x-axis is just like skewering that orbital right here. So that tells us then that we're looking at the 2px in this case. And so if it's the 2px, right, then that means that m sub l has to equal, plus or minus 1, right? One of the 2 of them. And so if it was a situation, where, which we're not doing in this class, right, but where it was like, okay, right, like give the definitive values, when you're looking at your answer for B and your answer for D, right, the m sub l values would have to be different for 2 of them, right? You just have to make a choice and say that one of them is going to be m sub l's positive 1 and one of them is m sub l minus 1 in these cases. So that's the thing to think about there. All right, so E. looking at this one, it looks pretty crazy and bananas compared to all the others, right? All the others have been, very simple. You have lobes and everything that are hanging out with each other. But you look at E and you have, two lobes that look like a p orbital, but then you have, two donuts essentially, wrapped in the middle of them. And so this right here, is going to be an f orbital, just as a spoiler. The way that we know that it's an f orbital, right, is that we can count the number of angular nodes. So the first most obvious angular node, right, is going to be the x y plane right here, right, because you're seeing that cut from the top blue donut down to the red donut in that case. The next thing to pay attention to is that as you start moving away from the p orbitals, you start to get mathematical combinations where you're not looking at perfect planes, but then you start getting these like cone-shaped angular nodes that are just simply a combination of two different nodes, right? So this right here, right, is what's generating that like donut shape with those two lobes on top, right? And that's actually a combination of one that includes, one mathematical definition of it, and then another mathematical definition of it, right? And they just simply got, squished together to turn into this like, hourglass type node that exists. But the important part to know is that that's not a radial node, right? That's an angular node. And the reason that we can distinguish the two of them is because we have this point right here, right, that's going through the origin, right, the point where x, y, and z are all equal to 0, right? A radial node doesn't do that, right? Radial nodes are never ever at the origin, right? Radial nodes are always outside of it, right, at some r distance away from the center in those cases. And so that's the distinguishing thing. And so again, this is just one of those things that you kind of have to initially memorize, where you're like, okay, right, like I see, one of those donut orbitals, I know it's going to be one of those really funky, D, F, G, blah, 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 right? Everything that's not S or P in those cases. And I know that two of the angular nodes are going to be caught up in that thing that forms, that vortex of nodeness that takes up that space right there, right? So when we're counting up the number of nodes in this case, what we have are 3 angular nodes, right? Because you have the two that are caught up in that hourglass node, and then you have the one that's the one that's like slicing everything at the, in the XY plane in this case, right? So there's 3 angular nodes in this case. We know that there's 0 radial nodes because, again, if we're looking at it, right, nothing has like a cap on it, right? There's no, as you move, as you're away from the origin, right, there aren't any nodes there where you're getting switches of, blue to red or anything, right? So there's 0 radial nodes here. And so now we know we have 3 angular nodes, we have 0 radial nodes, so that tells us then that L is equal to 3 in this case. So when L is equal to 3, what we're looking at is an F orbital. If we add up, right, the number of nodes we have, right, we only have 3 total nodes because there's only 3 angular nodes and 0 radial nodes. That means then that n has to equal 4. And so if n is equal to 4, right, we're going to be looking at the 4f in this instance. And so then now the question becomes, well, what is the directionality of what we're looking at, right? And so if we're looking at it, anytime, all of the ones that have like those weird, like the typical, lobes with the donuts on them, those are all the z direction in this case, right? So, if you ever look at the 3dz squared, right, you can see that that's that direction. In the case of the f, right, so the d1s are all quadratic, f becomes cubic, right, and then g becomes whatever the thing that you referred to for to the power of 4. And so forth, right? So in this case right here, right, what we're looking at is the 4f z cubed orbital in this case right here. So that's what that orbital right there is, right? And so then that tells us too, because we know that it's strictly along the z direction, right, that the m sub L value is equal to 0, right? Because it's along the z direction, right? There's no x and y components technically part of it. F, right? So if we're looking at F, what we can see first off is that we can see that we have one angular node, right, that's cutting there in between the the XY axis in this case right here, right? That's along the Z axis. And then we have another one that sits right here, right? That also cuts in between the XY axis and is along the Z direction in those cases, right? So we have two angular nodes. So that tells us what we're looking at is the L is equal to 2, right? Because there's two angular nodes in this case. We can see, again, that there's 0 radial nodes because there's no caps or anything like that on there. So then that means that n has to equal 3, right? So that tells us that this is a 3D orbital that we're looking at specifically. Now the question becomes, well, what is the direction? Right? What is the m sub L value, the possible ones that we can have for this system? So now looking at it, right, it sits, the lobes are sitting completely in like the X and the Y directions. Right? That's the directionality of them. They're sitting directly in the X and Y direction. So that tells us then that the m sub L value is going to be the maximum m sub L value that you can have, which in this case right here is going to be, plus or minus 2. The next thing right now to figure out, well, okay, there's two different combinations that you can have. You can have the x squared minus y squared, and you can have the xy, right? So those are the two different ones that have the m sub L plus or minus 2 value. So to figure out which one it is, the xy, right, is the one that sits in between the x and the y axis, right? Because you're multiplying the two of them together. So if you have positive x, positive y, right, you're going to get a positive thing. If you have, positive y, negative x, right, you're going to get in this quadrant, right, positive y, negative x, you're going to be right here. And then you have, positive or negative x, negative y, right, you're going to be over here, right? But they're all going to be sitting in between. Whereas the x squared minus y squared, right, is the one that sits directly on the axes. And that's what we're seeing right here is that it's sitting directly on the axes in this case. So that tells us then this is the 3D x squared minus y squared, right? So that's the orbital that we have right there. And so that's, the approach that you should take to any of these types of problems where it asks you to identify the type of orbital, right? To identify the different quantum numbers associated with that orbital, and identify the nodes, right? Is to look at, okay, are you seeing, color changes if it's one of the orbital, drawings that has those color changes, and seeing, okay, well, where are the nodes located, right? Where are the points where you're seeing that switch in color? And then being like, okay, right, does it cut through the xy, when x, y, and z are all equal to 0, right? If it does, that's an angular node. If it does not, right, if it's further out where that you're getting that change, right? Excuse me, that's then a radial node in that case, right? The number of angular nodes is always going to be equal to the L value. The number of, the principal quantum number is going to be equal to the total number of nodes that you have, right? So the number of angular nodes, the number of radial nodes plus 1, right, is going to give you the n value. And then, the m sub L value, you have to look at, well, where are the lobes that we're looking at, right? Where are those positioned? Does it have a z component to it? Is it only z? If it's only z, then, m sub L is equal to 0. Is there a little bit of z in there, right? Then that becomes a different number. And then if it's, there's 0 z, right? If it's all strictly along the x and the y axis, then that's going to be your maximum m sub L value. And so then you just have to figure out, like, what degree of z contribution do you have in those cases, right? But that's how you approach A5.